Welcome to the lectures on discrete time control systems, and today's topic is solution of discrete time state space equations, where we have the state space equations x of k plus 1 is equal to g into x of k plus h into u of k, and y of k is equal to c into x of k plus d into u of k, where we have r number of inputs and m number of outputs, right? And x of k is the state vector, x of k is the state vector, u of k is the input vector, y of k is the output vector. Now to find out the solution of these state equations, it is important for us to find out what is x of k, that is what is state vector. If we know x of k, if you can find out x of k, then y of k you can easily get it by substituting x of k here, and u of k is already known to us. C and d are our output matrix and direct transmission matrices which we already know based on the coefficients or the elements of matrices C and D. Therefore, output is depending upon x of k. C, D and u of k are already known to us. Therefore, if you find x of k, it is nothing but you can find out the output or the behavior of the system for all instants of time k from 0, 1, 2 up to infinity. So, to obtain y of k, you need to find out x of k. That is why x of k is called the solution of the discrete time state space equations. So this is nothing but x of k. X of k is a vector, it is an n by 1 matrix. X of k is an n by 1 matrix. So in order to find out that, first let us see how we can find solution using state in the continuous time domain. Let us see this, or we will just review what is the solution of continuous time state space equations. What is our continuous time state space equations? It is x dot of t is equal to a x of t plus b u of t, and y of t is equal to c x of t plus d u of t. Now considering this state equation, you can say that if I substitute x dot of t minus a into x of t is equal to b into u of t, I have rewrite this equation x dot of t minus a x of t is equal to b u of t, and multiply throughout this with e power minus at throughout this equation. If you multiply this e power minus at throughout, so what are we getting here? E power minus at x dot of t, where x dot of t can be represented as dx of t by dt minus e power minus at a into x of t, which is equal to e power minus at b u of t. Now when I integrate over 0 to t the entire equation or dt, here because I want to get the output as in time t, so I will represent the inner term with tau. If I represent it with tau, all replace t with tau when you go for integration, so that you will have tau, and d tau is equal to integral 0 to t. Again here also we can represent it with tau, so that once the integration is over, you are getting the result in t. Therefore, once you are going to see this one, d tau, then e power minus a tau dxt tau by d tau minus e power minus a tau a x of tau, you can say that we are having integral of this term gives e power minus a tau x of tau. That integration you can say, or to t, right? In fact, you can also say that d by dt of e power minus a tau xt e power minus a t xt can be written as e power minus a t, it is UV rule, u into dxt by dt plus xt into e power minus at into minus a. So you are getting this term there, minus a e power a t x tau. So this, if you are integrating it dt, I get this term. So dt and dt gets cancelled, d into e power minus at, that is what I have written here, and which is nothing but integral 0 to t e power minus a tau b u tau d tau. Right. So upon substitution of the definite limits, you can say e power minus a t xt minus, when you substitute 0, you will have x of 0. E power a 0, it is 1, or I, identity matrix, x of 0, you get this integral 0 to t e power minus a tau b u tau d tau. Right. So when I take this to the other side, I can say and divide by e power minus at, or pre-multiply with e power at on both sides, pre-multiplying with e power at on both sides and taking x of 0 to the other side, I will have e power at x0 plus e power at integral 0 to t e power minus a tau b u tau d tau. So this is the solution for the continuous time state equations. This is the solution for continuous time state equations. In a similar way, you can also, when you substitute x of t in this output equation, in x of t here, you will get the output. Here it is a combination of two terms. One is, it is representing or taking the values of initial conditions of the state vector and the input vector from 0 to t. So with which you are going to find our solution of the state equation x of t. And when this x of t is substituted here in the output equation, you will get y of t. So eventually you can get this solution of continuous time state equation. Now let us see, just attribute this to the discrete time state equation. In a similar way, we will be getting a result. So the output equation which we have got in the continuous time state space equations, x of t, which is the solution. What is that we got? X of t is equal to e power a t x of 0 plus integral e power a t minus tau b u tau d tau 0 to t. Now let us see whether we can get an analogous term, analogous solution here for our state equations, discrete time state equations. X of k plus 1 is equal to g into x of k plus h into y of k, h into u of k. Now let us say, go with the recursion procedure. Now what does this recursion procedure says? When k is equal to 0. This exists from k from 0, 1, 2, 3, so on. Now let us say when k is equal to 0, it is x of 1 is equal to g x of 0 plus h u of 0. When you are replacing k with 0. Now when you are replacing k with 1, I have x of 2 is equal to g into x1 plus h into u1. Now x1, if I substitute it here, I have g into x1 is this term. So g into x of 0 plus h into u of 0 plus h u into 1. This is what this x of 1 is. This one, h into u of 1 is here. So what is x of 2 for us now? G square x of 0 plus gh. When I multiply this with this, z u of 0 plus h into u of 1. Similarly, when I go with k is equal to 2, I have x3 is equal to g x2. When I am coming here, x3, k is equal to 2, I have g x3 plus h u3. g x2 plus h u2. Right. So now x2, what is x2 here? This is the thing, and this can be replaced here. So I will have g into g square, g cube x0 plus g square h u0 plus gh u1 plus h u2. So similarly, when you are going for x of k, you can just attribute this an analogous term. X of k can be written as, you can say, when you are following this one, you can say x of 3 is equal to g power 3. That is, x of k is equal to g power k x of 0, g power k x of 0 plus, you can say here, g square h u0, g power g into h u of 1 plus g power 0. That is g power, this is g power k, this is g power k minus 1, g power k minus 2 into h, g power k minus 2 into h, and g power 0 h u into 2. You can say this, and u of 0, here u of 0, that is, you can just simply sum up all these things into 0 to k minus 1. You are going up to k minus 1, that is 3 minus 1. This is up to 3 minus 1. That is what we are trying to say, right? From 0 to g power 0 to k minus 1. That is g power 0 to k minus 1. So I can write it as g power k minus j minus 1 into h u of j. For example, let us say we can represent this with, when k is equal to 3, here you can say g cube x0 plus sigma j is 0 to 3 minus 1 g 3 minus j minus 1 h uj. Now you can write this easily, g power 3 x0 plus, when j is equal to 0, it is 3 minus 1, so g square h u0, j is equal to 0, plus g power 3 minus 1, it is 3 minus 2, it is 1, gh u1 plus g3 minus, now it is k is equal to 2, 3 minus 2 minus 1, it is z power 0 h u2. So this is the equation. This equation is obtained here, x of 3. So this equation holds good for us. You can say this is the equation, or this equation is the solution for the discrete time state equation. discrete time state space equation. X of k is equal to g power k x of 0 plus sigma j is 0 to k minus 1 g power k minus j minus 1 h into u of j. Now you can see this is for discrete time state space equation and this is for continuous time state space equation. You can see these two equations can be compared and see that x of t is the solution in the time domain, x of k is the solution in the discrete time domain, right? And e power at x0, you can see this x of 0 and you can see u of t u of j from 0 to k minus 1, this is 0 to t, which is always less than the time that we are considering. So initial conditions here are considered in both the continuous time and discrete time systems, and u of t from 0 to t and u of j from 0 to the before instant k minus 1. When you want to find the instant at this particular time, the before instant up to that time, you require to know the values of the input. So you are getting these two relations in a similar way. So this is the solution for discrete time state equation, and once we know the solution or x of k, then automatically we will be understanding what is y of k, which is the output. We know that c into x of k plus d into u of k. That is, y of k can be obtained as c into g power k x0 plus sigma j is equal to 0 to k minus 1 g power k minus j minus 1 h u of z plus c into x of k plus d into u of k. So from this you can obtain c g power k x0 plus c sigma j is equal to 0 to k minus 1 g power k minus j minus 1 h u of j plus d into u of k. So this is your output equation. Right. So you have this equation in this form. Right. So you have the solution of discrete time state space equation, which is of that form, and the output equation in this form. So you are having this solution of discrete time state space equation x of k. When you know x of k, you can find out the value of the output at every instant for all instants of time, discrete instants of time. So with this in mind, we will go for state transition matrix. State transition matrix in the continuous time system is nothing but I'll just leave these two equations for us for our reference, so that we can see. This is for discrete time system and the other is for continuous time system. You can find out the state transition matrix. State transition matrix. You can say this is also called as the fundamental matrix. The state transition matrix or the fundamental matrix. Now in the continuous time domain, we have the equation x of t is equal to e power a t x0 plus integral 0 to t e power a t minus tau b u of tau d tau, which is what I have written it again in the continuous time domain. And the discrete time domain, x of k is equal to g power k x0 plus sigma j is 0 to k minus 1 g power k minus j minus 1 h u j. So these are the two equations that we have obtained in the continuous time domain and the discrete time domain. Now the state transition matrix. State transition matrix is a unique matrix, you can say, is a unique matrix which is of the order n by n, which is a square matrix, and you can call it in the continuous time domain, you can call it as phi of t, which is equal to e power at. Right, since A is a system matrix which is of the order of n by n, and e power at is also a matrix, you can have that as the state transition matrix. Now for a homogeneous equation, that is in the continuous time domain, x dot of t is equal to a into x of t. X dot of t is equal to a into x of t. That is a homogeneous equation when you are having input, when you are considering input u of t is equal to 0. When u of t is equal to 0, you can call it as a homogeneous equation x dot of t. Right. For this, the solution is x of t, which is nothing but e power at into x of 0. Right. This equation can be obtained from this equation because, for example, let me consider a dx of t, a single variable dx of t by dt is equal to a. A is a constant, for example, because it is a single equation, x dx by dt is equal to a into x of t. Right. Now if I cross multiply this, dx of t by x of t is equal to a dt. You can say that if you cross multiply this, x of t is brought down and d of t is brought up, then dx by dt, and if you integrate it over this function, you can say ln x of t to the base e can be written as a t plus c. A t plus c, or what is x of t from this? You can say e power a t plus c, or you can say e power a t into e power c, where e power c is a constant, or x of t is equal to e power a t into some constant k. Now at time t is equal to 0, you can say that x of 0 is equal to e power a0 is 1, which is k. Therefore k is equal to x of 0, and therefore you can say x of t is equal to e power a t into x of 0. Now this same equation is here when u of t is equal to 0. Right. So for a continuous time system, a homogeneous equation when you are considering x dot of t is equal to a into x of t, the solution for that is x of t is equal to e power a t into x0, which is this equation. X of t is equal to e power a t into xc. This is the solution for homogeneous state equation. Homogeneous state equation, x dot of t is equal to a into x of t. That is what we have obtained from this continuous time domain. Right. So considering this in mind, you can say that for the discrete time system, you can say we have x of k plus 1 is equal to g into x of k. This is a homogeneous discrete time state equation. Homogeneous discrete time state equation, that is when u of k is equal to 0. Now for this, its solution can be written as x of k is equal to any unique matrix psi of k into x of 0. That is what we are trying to say. X of t is equal to e power at into x of 0, where e power at is the state transition matrix in the continuous time domain. That is also a matrix. Therefore, we have considered psi of k into x of 0. X of 0 is as it is. That is, why do we call this a state transition matrix? Is it is state. You can say, what is state? It is the status of the system. Status of the system. Transition, what do you call by meaning by transition? What do you mean by transition? It is transforming the system state or the status or the behavior of the system from initial condition x of 0 to the final time x of k. Therefore, x of 0 to x of k, for transformation you require one unique matrix, and that matrix is called the state transition, and that matrix is called the state transition matrix phi of or psi of k. Right. So when you are considering this, we can have x of k plus 1 or x of k is equal to when you can substitute this here, you can have a state transition matrix psi of k, and this psi of k, when you are considering it, when you are comparing it with this equation, you can say it is g power k. Right. So g power k is the state transition matrix. When you are considering this equation and this equation, you can say g power k is equal to psi of k. Right. So psi of k is equal to g power k is our state transition matrix, or the fundamental matrix which can help us in the system states, all the n different system states, from transforming from the initial conditions x of 0 to the final time x of k. That is the reason you are calling it a state transition matrix or a fundamental matrix. So psi of k is equal to g power k is the state transition matrix, or you can say this is given as psi of k is equal to g power k, which is our state transition matrix. So for the continuous from the homogeneous equation, you can just represent this with, in the discrete time continuous system, you can say with our equations, x of k plus 1 is equal to g into x of k plus h into u of k. When you have this, you can just replace this with g into, you have x of k. X of k is equal to psi of k x of 0, right, plus, and you don't have this for a homogeneous equation, you have x of k plus 1 is equal to, now you have g into g power k x of 0, therefore you can write this as g power k plus 1 x of 0, or x of k plus 1, right, or you can call this as psi of k plus 1 x of 0, that is x of k plus 1 is equal to psi of k plus 1 into x of 0. That is, again you can say that we have, when you have x of k is equal to psi of k into x of 0, right, when k is the value, then you, for the next instant k plus 1, you will have this. So when you are operating on this, when you know the initial conditions, if you can operate on the state transition matrix, you will get the status of all the system states, status of all the system states in the next instant. That is why you can call this as the state transition matrix. Now when you are going for this, you can say, so g of k plus h of uk, when you are having this equation, the state discrete time state equations, and we know that x of k is equal to g power k x of 0 plus sigma j 0 to k minus 1 g power k minus j minus 1 h uj is our x of k. You can say when you are replacing this with that, then, or you can also call it as psi k x0 plus sigma j0 to k minus 1. You can call this as psi k minus j minus 1 h into uj, right, which is our x of k. And x of k, this is x of k, and when I replace this here, then I have x of k plus 1 is equal to psi of k plus 1 x0, because psi of k is g power k. When I multiply it with g into g power k plus 1, you get psi of k plus 1 x of 0 plus again g into sigma j 0 to k minus 1 psi of k minus j minus 1 h uj. Now this is our x of k plus 1, and we can have y of k is equal to c into xk plus d uk, or you can simply write this as c into psi k x0 plus c into sigma j0 to k minus 1 psi k minus j minus 1 h uj, right, plus duk. So this is what we are going to get in the outputs when you are going for state transition matrix for our non-homogeneous state equation. Now with this, we will try to go and discuss the Z transform approach of the solution of state transition matrix. The Z transform approach for the solution of discrete time state space equations, where psi of k is the solution of discrete time state equations. Now let us go with the equation x of k plus 1 is equal to gx of k plus h u of k, gx of k plus h u of k, and y of k is equal to cx of k plus d u of k. Now you have this non-homogeneous state space equations, and when you are applying Z transformations on both the equations, then I have, when you are applying Z transformations to this and to this, you have Z transformations everywhere. In both these equations, you have Z transformation of x of k plus 1 is given as z into x of z minus z x of 0. This gives us this one, and which give us g is a constant, x of k you have x of z transform of x of z plus h into u of z, right. And with this, what we can do, you can just convert this. Z is a complex variable, therefore z into I, when I consider x of z and x of z common and I bring it to the left hand side, I have gi minus z x of z is equal to, and I take it to the right hand side, it is z into x of 0 plus h into u of z. Right. Now if I multiply this, if I pre-multiply with zi minus g whole inverse, and when modulus of zi minus g, when gi minus g not equal to 0, right, the determinant of zi minus g should not be equal to 0. When this happens, because you need to find out the inverse, therefore if I want to find x of z, I will have zi minus g whole inverse into Zx of 0 plus Zi minus G whole inverse into H u of Z. H u of Z. That is x of Z for us. Now to find out this equation, if I go for inverse Laplace transforms, or to get the output y of z, once we go and take this, we get z transform of y of k. I have y of z, which is nothing but z transform c x of k. It is c into x of z plus d into u of z. Now considering these two equations, you can say to get the discrete time domain in the k domain, I need to go for inverse z transforms. When I go for inverse z transforms, this equation can be written in this way, that is x of k, inverse z transform of x of z gives me x of k, which is inverse z transform of zi minus g whole inverse into zx of 0, z into x of 0 plus inverse z transform of zi minus g whole inverse into h u of z. Now this is our output. This is in the k domain, right? X of k, or the discrete instant. Now what is x of k? X of k is nothing but g power k x of 0 plus sigma j is equal to 0 to k minus 1 g power k minus j minus 1 h u of j. Now comparing these two equations, equations 1 and 2, when you compare these two equations, you can say that g power k is nothing but this x of 0 and x of 0. Therefore g power k, which we have already discussed that it is psi of k, which is the state transition matrix, you can call this as z inverse of gi minus g whole inverse into z. Gi minus z whole inverse into z. And what is this equation? That is sigma j is equal to 0 to k minus 1 g power k minus j minus 1 h u of j is equal to z inverse of gi minus g whole inverse h u of g. Right. So with this equation you can say that g of k, which is the state transition matrix, you have psi of k, which is inverse z transform of gi minus g whole inverse into z. That is, the state transition matrix is depending upon only all the elements of G matrix or the system matrix. It is not at all involving, or it is invariant. State transition matrix is invariant with the all other matrices, that is the input matrix, the output matrix, or the direct transmission matrix, that is H, C and D matrices. It is dependent only on G matrix, that is the system matrix.